Yeah, thanks for the great introduction. So it's always wonderful to be here in Arizona, and particularly this time because you don't have 2 feet of snow on the ground. I'm coming from Connecticut. So that's awesome. But the other awesome thing about coming to Tucson that I really enjoy is to visit this place, because this place has a very unique culture. And it also has a lot of people that are very smart. And in fact, I'm going to go out on a limb here and say that everybody sitting down right now is really smart. They don't get, okay, nobody's disagreeing with me. So we'll start with that. So everybody's here really smart. Wonderful. But are you creative? Are you innovative? And that's the question that we're going to explore today. And I want to just start by asking, how many of you consider yourselves to be an inventor? Just raise your hands. I'm an inventor. Well, we got a few people. Yeah, that's good. So you're at a block party, you're having the tequilas and tacos, and someone says, what do you do? Oh, I'm an inventor. I think we have a little bit of hesitation in part answering that question because we're not really quite sure what it means to be an inventor and what an invention is. And sometimes even if we invent something, we might ask ourselves, did I invent that? And that's the topic for today. So I'm going to start this discussion with what I consider to be one of the most important and significant innovations in optics and photonics ever. We'll pause for a moment and guess what that might be. Here it is. Now, for the younger people here, this is called a light bulb. And the way this works is a little wire in there and you pass electricity through it, and it gets so hot that it glows. And if you design it well, it'll glow so brightly you can illuminate an entire room without any semiconductor devices at all. So an incredible invention that actually changed the world. So now the next question is, who invented the light bulb? Any ideas? I'm going to shout it out.
Edison.
Well, Edison. Okay, fine. Let's go with Edison. So Thomas Edison, we're all good Americans, and Thomas Edison invented everything, including the internet. But there are a lot of people who would dispute that, and not just because he's an American. The reason is there were no less than 22 inventors ahead of Edison that described what I just described. A bulb with a wire in it, and you heat it up and it glows and it lights up the room. Here's an example. This is 1840, Warren de la Rue, an incandescent platinum filament inside a vacuum bulb. He heated it up and it glowed and it lit up the room. So this was almost 40 years before Edison presented his light bulb. So why do we keep giving Edison credit? Well, it goes to this question of, well, what is an invention? So we need to define this. So you could ask Siri or Copilot, but you could also ask a dictionary. And this is a very good definition, actually. This is Merriam-Webster. An invention is a useful device or process created for the first time through imagination or ingenious thinking and experiment. Well, I managed the Zygo portfolio for decades, and I can tell you the patent office doesn't care anything about how imaginative you are or how ingenious you are. It's got nothing to do with it. What matters is that it is useful and you're doing it for the first time. Those are really the two key things you have to keep in mind. Now, it might require imagination and ingenious thinking, but that doesn't make it an invention necessarily. So what did Edison get right in this context? Well, it was certainly new, but what was new about it? It was an affordable, long life, high resistant filament that made this light bulb work. The high resistance part, some people don't know this, that allows you to have light bulbs in parallel because you can drop the voltage from light bulb to light bulb. You know the old Christmas lights where one would burn out and then the entire string would burn out and you have to throw it away? Well, that was because every previous light bulb was a low resistance filament. The other thing was he worked on the vacuum equipment to have a very, very high vacuum. They were never sufficient before. And finally, he came up with a complete system. It wasn't just light bulbs. So that is something he got right. That was all new. And also it was, of course, very useful. So this is just a few years after Edison invented the light bulb and New York City was lit up by lights. So useful and new, definitely. He came up with the first practical lighting system. So I would argue that, in fact, he invented the light bulb. But it did rely on innovations that came before. He studied all of those 22 inventors that came before him. He knew what they did. He knew what worked and what didn't work. He also had a team of inventors, or a team of coworkers that helped him make it happen. So this gets me to think about my inventions. So Florian mentioned I have 140 patents. and 3 good ideas. But this is the, at Middlefield in Connecticut, this is the Zygo patent shrine. And if you come to visit us, you must first bow to this patent shrine. And a lot of these patent plaques are in fact mine. But are we talking about new and useful things? That's the self-doubt that comes with any inventor. To answer that question, what I'd like to do is to guide you through some examples of my inventions and where the ideas came from, and in some cases, what happened to them. And they're not cherry-picked. Some of these are inventions that were very successful. Some of them weren't. And there's one of them that's not even an invention. So that's my plan. Sound like a good plan? Okay, good. Let's start with a new interference objective. And to launch this discussion, I will let you know that I retired from full-time work in 2024. And so we had 3 retirement parties. This is one of them. At one of the retirement parties, I was gifted this beautiful cross-section of the Zygo wide field objective. So Jim Began and I invented this objective, and the engineers got together and sawed it in half and put it back together again. They gifted this to me. Absolutely wonderful. So I look at this, and I go, okay, what was so clever about this idea? What was so ingenious and imaginative? If you look very closely, you will see the basic idea is 2 tilted coaxial plates to form an interferometer. There's a beam splitter plate and a reference plate. And they're a little bit tilted. And that's it. Did I invent that? That's the question. Well, I think I did because we have patents on it. But let me just explain to you where that idea came from. And then maybe you can tell me later on afterwards with some coffee. So I think all of you have some idea what an interferometer is. Many of you are experts. Many of you have designed interferometers, but perhaps what isn't quite so well known is interference microscopes use interference objectives. They're basically grossly overpriced technical microscopes with interference objectives attached to them, and you get interference fringes from that. So they're very convenient, and there are principally 2 types of objectives. This is the so-called Michelson objective, and this is used very frequently for low magnification. For example, a 5x objective that has a 3 millimeter field of view. And you see that little thing sticking off to the side, that's the reference mirror. The other type of objective, which doesn't require a prism, which is a problem at high magnifications, is called the Moreau. So Miro invented this in the 1940s. Very clever idea. He realized that at high magnifications with incoherent epilumination, you can steer around a coaxial reference mirror. So now you don't have to have the reference mirror off at the side, and you don't need to have that big prism. Wonderful idea. So that's about it. So occasionally you run across a specialized interference objective, might be a Linux or something like that. But basically the world of commercial interferometry is Moreau's and Michelson's. So is that sufficient? Well, not really, because sometimes you need other things. You need to be able to measure parts that are really big flat parts, and you'd like to do them on your interference microscope because you paid for it. So it's got a nice platform, it's got all the electronics and software. But maybe you want to measure an optical flat for surface texture, maybe you want to measure this industrial part, which is too big for that 5 millimeter or 3 millimeter field of view. This is 40 millimeters. So that's the task. We want to make an interferometer that will allow us to measure something that big. Now, if you just scale up an interference microscope objective, it looks like this. So that's something that we call Thor's hammer. We built this. It's a half-X objective. It's 28 centimeters tall, and it's extremely heavy. And in fact, we only made 1 or 2 of them because they're really not very practical. So what's the thought process? Well, let's go back to the Michelson interferometer. We know that this is a great geometry. We start with this, and we can see that if we carefully adjust this, we can even get interference fringes in white light. So that's great. But because it's asymmetric and it's sticking out this way and that way, it's not really suitable to be an interference objective. Now, thinking about the Moreau objective, but trying to figure out how to do it at low magnification, we just need to rearrange things a little bit. And so there you do. You got two plates, they're both semi-transparent, and now the reference mirror is semi-transparent rather than having a nice blotch on it. And you angle them a little bit. Now you do get some spurious reflections, but it turns out you can easily block those, all of them, just with an aperture, and you get 100% fringe contrast in this objective. What does that look like in the geometry of an interference objective? Looks like that. Again, very simple, 2 plates, 11 worldwide patents. Now, this is the design of that half-X objective, now converted into this SIGO wide field objective. Now, instead of Thor's hammer, we call it the champagne bottle. And you can use this for all kinds of things. For example, you could measure the 3D topography of stacked planar waveguides, very interesting for augmented reality applications. But that objective is very useful, but it's not our most popular one. The next one is the most popular objective that we sell. It's the 1.4x ZWF. The reason why it's so popular is because it has a 12 millimeter field of view, but it's paraxial. What does this mean? It means you don't have to refocus to go from 1.4x all the way to 100x. And that's only possible if you use this ZWF geometry. You can't do it with a Michelson, and a Moreau won't work either. So that's what that kind of a range looks like. You can see the expanded portion at 100x compared to 1.4x, and you just tell the software to rotate the turret. So that is an extremely popular design. So new and useful. Now it has a specific characteristic to it. The patents all actually are titled equal path interferometer. Why? Well, because it needs to work with white light. Why does it need to work with white light? Well, I'm going to tell you. The reason why is because we want to do coherent scanning interferometry. Now, I didn't invent this. A lot of people did. Matter of fact, Florian's professor and advisor at Erlangen is arguably the father of this idea. But many people contributed to development, and I would like to think that I contributed as well. So let me tell you the story of coherent scanning interferometry, because this is by far the most popular and powerful technique in interference microscopy today. So if you go back a little bit to the 1980s, most interferometers used lasers. Matter of fact, we had an interference microscope and it used a laser. So the white light interferometers basically had become defunct practically, with a few exceptions. Now, a single wavelength laser interferometer is great for smooth surfaces. If you get nice, beautiful interference fringes, you can interpret them fairly easy. But the problem is that most of the world is not smooth. Most of the things you want to measure are not smooth. So 1990, worldwide market for interference microscopes was maybe 100 or 200. So not really much of a market. Whereas the applications are certainly much greater than that. If you have a rough surface, what you end up with a laser light is these speckles. It's speckly laser light, and it's very difficult to interpret. So you only have these mirror-like surfaces, and we were asking the question, can we measure a wider range of parts? So I was engaged in this research at the time. I remember we were trying to figure this out. So all right, so here you say, okay, what possibly could we leverage that's already known and come up with something which is new? At that time, there were already people experimenting with optical coherence tomography. It was very slow. People used pig's eyes. They didn't use real eyes because they had to blast the light into the eye. It was a destructive test. But people were working with optical coherence tomography. And the miracle about optical coherence tomography is you actually don't need to interpret interference fringes. You just have to see where they occur. So you get this signal. It's almost like an optical radar. And then you can have a cross-sectional image like this. It's called a B-scan. This is of a person's cornea. Matter of fact, it's not just any person. This is my cornea. It's my left eye. I had this taken before an intraocular lens was put in, and it was absolutely perfect. At the end of my doctor's visit, I went to the front desk and I said, can I please have those OCT images? And they said, no one has ever asked us for that. I want it. So I have these and I use them frequently in my lectures. Okay, so what is the idea? The idea around 1990, and this was Thomas Dresel was doing his Diplomarbeit in Erlangen, and the idea is to apply that basic concept to surfaces, to rough surfaces that have very confusing fringes, but you're only looking for the interference pattern. And if that's the case, then for example, in this case, when we're looking at a rough surface, you see as we scan the interference objective from top to bottom, the interference pattern coming and going. So as the interference pattern comes and goes, you record when that happens, and that tells you what the surface topography is. Simple idea that I can tell you I worked on this problem for 3 years. It never occurred to me. So it actually is a brilliant way to manage it. So what happened to this idea after it was published? The first rough surface tester. The first interference microscope that used this technique was at Wyco, 1992. It was called the rough surface tester, truth in advertising. And it used firmware to demodulate that signal. So great. So that's so you can see things are now starting to move. We're going to take this technique further. Now there was a basic problem with the way that instrument worked. It had firmware in order to demodulate the signal, but now you basically have thrown away the interference fringes. And the interference fringes underneath that yellow envelope are quite powerful. They're much higher resolution. So you'd like to be able to use both those fringes and the fringe contrast as a way to measure surfaces. The basic problem, and it's actually kind of a sophisticated problem for a metrologist, is that those two signals have completely different fundamental metrics of length. The contrast is based on how fast you scan. Whereas the interference fringes, well, that depends on the wavelength, it depends on how, the magnification of the objective, it depends on the camera spectral density, a whole series of things, optical coatings that have nothing to do with the scan speed. So two completely different ways of measuring the part, and it's the same part. So they disagree with each other, and trying to get them to work together is very difficult. Okay, so that's the problem. You're forced to choose with either contrast or phase, and the answers are different. So I was thinking about this, and I read this paper on fiber sensing where people were trying to look at index changes in fiber sensors. And they said, well, look, if you take your interference signal, which is on the left, and you go ahead and you convert that into the frequency domain using a Fourier transform, here's what happens when that signal moves back and forth with the scan. So you end up with the phase in the frequency domain is going up and down, is changing position or changing slope. So the position of that line is the interference phase, fringe phase, and the slope of that line is the fringe contrast. But they're both connected to the fringe frequency. The fringe frequency is how fast do the fringes go by. And how fast the fringes go by is determined entirely by the scan. So now both of those signals, the interference fringes and the interference fringe contrast, are linked together by the fringe frequency, by the scan. They have a common metric. So the objective scan speed becomes the same for both methods. So now you can use both of them almost interchangeably, and it's fairly straightforward in the software to do this. You can fringe contrast for rough parts, like that additively manufactured part, and you can also use the fringe phase for smooth parts. And that was the innovation that was my first project at Zygo. And in 1994, we introduced that instrument. So that instrument went on to be refined. So we still make that. It's still called the New View, but it has evolved significantly since then. And that particular idea has generated $1 billion for the company. So useful as well as new. All right, so that's that idea. Now, $1 billion is a lot of money. Not all ideas produce that kind of money. They might not produce any money. And it doesn't necessarily have anything to do with how clever you are. The market doesn't always appreciate that. You could be really smart and they don't really care because you're asking people for money. So I'm going to give you a couple of examples of really clever ideas that were ingenious and imaginative, but ultimately we don't make them anymore. The first of these is going to be a description of a micro ellipsometer for data storage disk drive. So the context here is computers. So let me take you back again, 1995, because this is a history lesson. 1995, you just got this new computer delivered at the house, and it's running Windows 95. So you've got the very latest software. But the thing which is most impressive about this computer that you just bought for about $3,000 in those days is it had a 1 gigabyte hard drive of storage. Incredible. I'm not talking about random access memory here. I'm just talking about the disk drive as a gigabyte hard drive. So that was an incredible amount of memory space for those days. But that was really not enough for most of us. We looked at the disk drive and said, can you put in some more? Because now I can store movies and things like that on my computer. How do you get more? Well, in order to get more, we need to take a look at how disk drives work. So how do you store information on a disk drive? Well, disk drives run at about 10,000 RPM, which is amazing. And there's this thing, the read-write head, which I'm showing here, and it's flying above that disk, literally flying above that disk. And it's only about 25 nanometers away. And that was in the mid-1990s. So it's skating along this disk at this incredible speed, and is held in place by these hydrodynamic forces. Now, if you want to get more information stored on that disk, you might want to get closer. So, okay, let's design something which is getting closer, but how do we know that we've gotten closer? How do you measure that? Well, you want to measure it, but how? The slider is underneath a magnetic disk and it's 25 nanometers away. You're not going to get in there with a pair of calipers and measure that thing. It's really, really difficult. So what's the solution? Well, a solution, no one will guess this, where the solution comes from. But what you have to do is ask a railroad engineer. And why? Well, railroad cars, their wheels are held in place by these lateral thrust bearings, even today. This is a steam engine, but that's just the way they work. So you have thrust bearings, and thrust bearings are these different pads. And lo and behold, if you look closely at this, there is something which they call a slider. And the slider presses against the thrust bearings. And they have the same problem. They have a lubrication issue with the thrust bearings, and they need to determine how high that slider is flying above these rotating pads that are holding the wheels in place. So there was an Australian railroad engineer in 1921 who thought about this. He said, I know what to do. In my basement, I'm gonna replace that thrust bearing disc with a glass disc. I'm gonna use water power from my faucet to drive a little wheel, which will then be connected to a turntable to spin that disc. And then I'm going to look at the slider and how it interacts with that disc optically. So you got a slider and you got a surrogate glass disc, and now you see interference fringes. And it's a wonderful paper, again, 1921. He used sodium light and he was able to count up the fringes and change the speed and see how the slider changed its height and so forth. So let's do that. Why don't we do that? Well, part of the reason is that as you get really, really close, just looking at the interference fringes isn't enough. So what we invented was a way to do that ellipsometrically. So we treat the air gap as a thin film, and that gives us maximum sensitivity at contact. It also gives us the ability to compensate for the optical properties of the slider in situ because it's an ellipsometer. So this is the diagram. I won't walk through this diagram. I just want to impress you with how cool it is. It's a 250 kilohertz polarimetric sensor to do dynamic ellipsometry of this little teeny air gap. And this was 1996, 1997. So we built the machine, looks like this. So there you can see the glass disc and you can see the sensor. This was called the Zygo Pegasus. We patented it. We made a product. One of the interesting things about this problem, or interesting things about this product, was that at some point we had to specify the annealing properties of the disc for the supplier. And the mechanical engineering at Zygo at the time, Jim Sabitsky, comes to my office and he says, how much birefringence can you tolerate in this disc? And I said, we can't tolerate any. It's an ellipsometer. We're looking through the disc. And he said, you do realize this thing is spinning at 10,000 RPM. Oh, a glass disc spinning at 10,000 RPM wants for all the world to fly into a million pieces. It's under enormous stress. And stress birefringence turns out, in this particular case, to be about half a wave. So it's a 10,000 RPM rotating wave plate that we have to look through. Now, when he asked me that, this was how far we've gotten on the product. And it was my idea. So I had to come up with a solution pretty quickly. And I wouldn't tell you this story, but I found it otherwise. But I did figure out a way to do it. I figured out a way to characterize the entire disk while the disk was being loaded into position for the next part. Every time it was loaded into position, the ellipsometer would measure the refractive index properties of the disk. And it's a refractive index tensor, so it's quite an interesting physics problem. Probably the best physics I've ever done, and I did it in 30 days. And we coded it, and it solved the problem perfectly. So that we were able to make these types of measurements where you could look at the leading edge, the middle part of the slider, and the bottom of the slider. As you increase the spin speed, you see it coming up. Fantastic tool, state of the art, best one in the world. So what happened? Because we don't make this instrument anymore. Well, what happened had nothing to do with how imaginative and ingenious and clever this idea was. The disk drive market changed. People wanted $80 disk drives, not the biggest disk drive they could buy. At that point, no one wanted to buy the state-of-the-art technology for measuring disks. And so it ended after a few years. We sold a few, but the production stopped. Heartache. But the heartache's not over because I got another invention from the same time period. So flatness tester for machine surfaces. This one is very geometrical, so it's really clever. How to make a disk drive platter. So we talked about measuring the flying height. Well, the platters themselves are these magnetized aluminum discs, and the aluminum discs are basically stamped out of rolled aluminum. And rolled aluminum is brush finished. It's not a mirror-like surface at all. It's the kind of piece of aluminum you find at Home Depot. But these discs have to be flat to 10 microns, better than 10 microns, before you put the magnetic coating on them. So they have to be tested for flatness. But they're not smooth enough to be tested with a laser piezointerferometer. And they are too flat to be measured, at least with the structured light technology that was available at the time. So there was no way to measure these. People were trying to do it mechanically. It was a big unsolved problem. So I tried with the other guys in research to come up with a solution. We tried everything. We tried infrared interferometry. We tried grazing instance interferometry. There were all kinds of things. A list of 7 different things that we tried. None were very good. We were very unsatisfied. And then I did what you usually do when you have no more good ideas left. You pack your bags and you go to a conference. So this was at a conference in Frankfurt in 1994 called Optics and Productivity and Manufacturing. And there was this guy there, Pierre Jacot from Lausanne, and he gave a talk. And because it was 1994, that talk was done with an overhead projector, now becoming as old as the light bulb. Now, it was a good thing that he did this with an overhead projector because he was able to do something very interesting. He reached into the pocket of his coat and he pulled out an aluminum blank, and he pulled out something else. He pulled out something that he called the magic plate. And I have one with me afterwards. We can play with it when we're having coffee. You take the magic plate, you turn on the light, and boop, up pops 12 micron interference fringes on a rough surface. You just held it up. So I about fell out of my chair. And so afterwards, I went up and I grabbed him by the collar and I said, I have to see this thing. Went to Lausanne. He gave me a bunch of plates, including one that's this big, that work this way. So what is this magical plate that if you hold it up to a rough surface part produces interference fringes that are 12 microns synthetic wavelength? Well, it is a hologram. It was a holographic collimator. And if you take a holographic collimator and you put it up against a part, you end up with a first order and a 0th order diffraction pattern. And they are aimed at the surface at somewhat different angles, about 10 degrees in this particular case. So you have these 2 beams. So these 2 beams, both of which go to the part, are then recombined by the same holographic collimator, and back at the camera, those fringes are formed by the interference of those 2 beams. So both the measurement and the reference beam basically are going to the part. Absolute genius. So fantastic. And at that time, they were busy trying to figure out how to get anybody in the disk drive industry interested in this. And they all said, we can't use this because there's a serious flaw. And the flaw is that the holographic plate has to be in contact with the object in order for it to work. And that's not practical for automated testing. We need to test these things, hundreds of them every hour. We can't be fooling around putting things in contact and looking at them with an overhead projector. That's not industrial metrology. So I took this idea and the plates from Pierre Jacot and I brought them home. And I invented a dual grading geometry. And in this geometry, you can see the light going through. It does the same thing. It's 2 linear diffraction gratings, and the light is directed towards the object, the surface S, at 2 slightly different angles, and then they're recombined. And this does exactly the same thing, except that there is now a working distance that can be anything you want. It's the same as the separation of the gratings. It looks like this in 3 dimensions, 12 micron equivalent wavelength, 50 millimeter working distance, 100 millimeter aperture. It's visible light. It doesn't even have to be a laser or anything. It works with any light. Because the phenomenon is achromatic. So kind of miraculous. So we made a machine that would work this way, and we automated it. And it had the appropriate gauge repeatability for a 10 micron tolerance of 1/10 of a micron. I found this, for this occasion, I found this old video and rescued it from a VHS tape. So that was the Zygo flatness tester for disks. We called it the Mesa product. 720 disks per hour. So what happened to this product? Well, I already mentioned the cost of disks, but it was even worse than that because this was a very affordable tool. There's nothing in it. It's not like the ellipsometer thing. It was really expensive. The problem here was we sold one to everybody who was manufacturing disks. And when we were done, which was a couple of hundred, that was it. They would say, okay, well, we need to move into a different market. And there just wasn't one at that time anyway. It was a big success for data storage. It solved the basic problem. But just as with Flying High Tester, the demand started to decline, and then we eventually discontinued the product. Now, this particular idea, it frustrates me a little bit because I think there could be applications here for other things like machine metal parts. And maybe there's someone in the audience who will get inspired and revive this concept because it really is kind of cool that you just direct the two beams at the same time to the part and you get this kind of neat effect. Okay, so those were examples of what I think were pretty ingenious ideas that were ultimately failures in the marketplace. We all got to feel bad about ourselves. I'm only half kidding there. It is difficult. Joanna knows what I'm talking about. So let's make things a little bit more upbeat, but with an example of a simple idea that had a huge impact, even simpler than the first idea that I showed you. But it's an idea from an industry which is not very simple. The application here is semiconductor photolithography. So everybody has semiconductor devices. We can't be separated from them anymore. Between cell phones, computers, everything, self-driving cars, whatever. If you look at the size of the separation between feature sizes in the semiconductor industry, it is just unbelievable. The next nodes is the 20 angstrom and 18 angstrom node. So we're talking about feature separations of a couple of nanometers. So that's well beyond the resolution of an optical tool. You can't even see it. Now, you have to manufacture those in some affordable way on these giant machines. And these machines look a little bit like this. It's highly simplified, where you have a reticle, or so-called mask, which has the pattern that gets projected onto the wafer, and the wafer moves back and forth, and you project it all over the wafer. And you do that 46 times for the different layers of a semiconductor wafer. And then the wafer becomes this very, well, it becomes a piece of money. And you pay for those things by producing them accurately in large numbers. Now, because it requires these motions in order to produce a wafer, stage metrology is extremely important. And since the beginning of time, when we were all children, this was all done using heterodyne interferometry. It's the only way that you can get the kind of precision for those stage motions, because you have to know where those stages are to 10 times better than the tolerance, which is nanometer. So you need to know where the stages are to a fraction of a nanometer, and the stages are moving it up to 8 meters per second. They're going like this. I'm not even moving my hand fast enough. And during that entire time, you have to know where the stage is to a fraction of a nanometer. So it's done with heterodyne interferometers. So I have this detailed picture here, but I'm not going to walk through it. It's much easier to do an animation. And you can see how if you move the stage back and forth, the interference signal, which is a continuous signal, moves back and forth as well. So you can tell from the yellow curve there in electronic signal processing where the stage is. And you can do that to a small fraction of a nanometer. Matter of fact, you can do it with noise levels measured in the tens of picometers. That's how powerful heterodyne interferometry is. But there's a basic problem here that people started to encounter, well, around 2000, and it became critical around 2010. And the problem is that interferometer is looking through the atmosphere of the photolithography tool. And it might be nitrogen or what have you, but nonetheless, it's some kind of a gas. The gas is moving around. It's turbulent airflow. And that destroys the quality of the measurement. You can say, I got 10 picometers of noise. Yeah, but you've got 40 nanometers of air turbulence distortion in the result. My stages are going all over the place, and I'm no longer making any money. So this was a very serious problem. Lots of ideas on how to fix this. it turns out that the best solution is to move to optical encoders. The reason why no one thought about that before has to do with things like Abbe offset errors. If you're a metrologist, you know exactly what I mean. It is actually much more difficult to implement an optical encoder solution, but there was no other option. And there's only one thing more powerful than physics in this world, and that's the marketplace. Semiconductor industry cannot slow down. So they said, okay, we can figure this out, but you need to supply us with an encoder. And that encoder is going to measure a grading position, which will be attached to the stage. It'll have reduced air path, and will have much lower random errors. So what does one of these gratings look like? It looks like this, these huge two-dimensional gratings. And these things are attached to the stages, which are, again, moving back and forth at 8 meters per second. And then you need an optical encoder to look at that grating. And in 2010, commercial encoders had nowhere near the precision to do this, because you actually get a desensitization when you're looking at the gratings. You need better than conventional measurement accuracy to do this. So how can we do this? Now, the time scale when this finally came up and the research group was asked to solve this is we had very little time. We already manufactured heterodyne interferometers. We're one of the major manufacturers of stage positioning metrology in the world. And so we sell into that market, the photolithography market, this design that I showed you before. So we have all the lasers, the electronics, all of the optics, it's all ready to go. How can we make an encoder with these building blocks? Well, it's pretty simple. You just move the object so in such a way that you now have a grating. You're looking at a grating, and the diffracted light goes to a prism and then goes back to the grating, goes back into the interferometer. Now, when the grating goes back and forth, up and down, in this situation, you see the signal going back and forth. So just rotate this whole thing and look at a 2D grating. That's all it is. And believe it or not, we were able to patent that. That idea had not been patented or published before. So now encoders dominate front-end wafer metrology, not just because of us. Heidenhain is the major market in encoders. I don't want to misrepresent it, but we are a major manufacturer of optical encoders. It's a big part of our business. Maximum velocities of 8 meters per second. The digital resolution is 7.6 picometers. Now, I wish I could show you data from this thing. I'm not allowed, but I can show you data from the other guys. This is from 2010. This was data published by ASML. And I only show this, I just love this picture, even though it seems like it's out of date. This is now 16 years ago. But if you look at these two graphs, the upper graph shows the effect of air turbulence, which at the time was considered to be fatal. So ghastly, so horrible, that you would not be able to make any wafers with it. So you look at the excursion there, the scale is plus or minus 1 nanometer. That's the contribution of the air turbulence inside the photolithography tool. And that was a fatal uncertainty to the measurement. And then the lower one is what happens if you go to an encoder. And that's why all of the high-end immersion lithography tools use encoder technology now. So that was a very simple idea. We later came up with a whole bunch of other ideas that were even more sophisticated for different types of situations, but that really launched the encoder product line at Zygo. And honestly, it was a drawing that I made in PowerPoint and sent by email to someone. Said, what if we did this? So that's an example of, nowhere near the birefringence compensation idea in terms of cleverness. So now to finish this up, to wrap this up, I want to provide you an example of an invention that is not an invention. And it kind of addresses the question of whether or not everything needs to be an invention. So I've always felt the need, because I'm an inventor by heart, everything has got to be new. And if it's not new, it's not worthy of being worked on. And it ain't always the case. It can sometimes be crippling to think that way. So I'm going to tell you about the way we develop dynamic laser photo systems using tilt fringes. So if we go back to the definition of an invention that I had at the very beginning, it's a useful device or process created for the first time through imagination or ingenious thinking and experiment. And we decided that useful and new for the first time are the two things that a patent office will look at. And it's the two things that really have to be there for it to be an invention, even if it's a simplistic invention. But what if it's merely useful? Is that okay? You might be you might be a little bit more humble in describing it, but nonetheless, it probably, if it's really useful, is going to be arrived at through some thinking and experimentation, maybe a lot of work. So let's take a look at a modern phase shifting Fizeau interferometer. So the way these things work is they're heterodyne systems as well. The heterodyning is done by a mechanical phase shifter, which moves back and forth. You can just barely see it there. There's an arrow, and it shows the reference mirror being moved. The interference fringes move, and you can interpret that result and get an answer. The problem is that you're acquiring data over time. And if you're acquiring data over time, the error is flowing, and you've got the same problem that I already outlined with the previous example. The error spoils everything. And if you look at an interferometer in many environments, it's like this. This is actually not uncommon. This is a pretty common type of thing. And you look at that, and for a metrologist who's used to doing phase shifting interferometry, that's not a very attractive picture, that airflow. That's going to create a lot of errors. So people have known this for a long time. Solutions didn't really start appearing until after 2000, even though, and I wish at some point I'm going to have enough time to do an entire talk on this, the history of how this was solved with polarization is quite interesting. So polarized phase shifting, there's a lot of that going on here. I've seen a lot of labs where it seems like that's one of the pieces of kit that you get. When you sign on as faculty, they give you your badge, and then they give you a instantaneous phase shifting camera. And it's a fantastic idea where instead of doing the mechanical phase shifting, you use polarization tricks to create 4 or more phase shifted images simultaneously, so all in one shot. And you can even put all of those images on one camera. And you can do that with clever pixelated cameras and so forth. This idea, believe it or not, dates back to the origins of holography. It was first done by oh goodness, the inventor of holography was, sorry?
Dennis Gabor.
Dennis Gabor, yes. Dennis Gabor came up with a polarized phase shifting holography system in 1958. But again, most people don't know that, forgot about it. But it eventually ended up to this point where people have these polarized phase shifting cameras. Now, this is such a great idea. And even though it has a history to it, no one was really using it before then. That this is one of the few times when I thought, I wish I'd invented that. That'll be a different talk. I'll talk about all the inventions that I didn't invent, but I think they're absolutely brilliant. So this is a fantastic invention. I didn't come up with this. Some people that you may know were involved in bringing this technology to market in a successful product. Very much an Edison story, but in dynamic phase shifting interferometry. So yes, that's Jim Wyant. It's kind of an odd picture there. What's he doing? Well, he's writing with Tammy in Schnooky. So for years, we used to tease him every time about, hi, Schnooky. This was in Spiewald in 2013. We were canoeing in Germany.
We need to translate Schnooky.
I'm going to let you do that.
I will try to come first.
Okay. Yes, Schnooky. Well, anyway, now there is another alternative which is also rooted in holography. And also here, many of you know who Mitsuo Takeda is. He's still alive. He's still with us, thank God. Wonderful, wonderful person, and also a great contributor to optical metrology. And he had this idea in 1981 of applying the ideas behind off-axis holography to fringe projection metrology and for interferometry generally by transferring things into the frequency domain. So you have off-axis holography with tilt fringes, and then you can get the same effect, instantaneous phase measurement using a spatial carrier. And that means that you collect all of the information you need to get the data in just one camera frame, just like the polarized camera, except you don't need a polarized camera. All you do is introduce tilt fringes. So here's a laser Fizeau interferometer where the reference has been tilted. You end up with a bunch of tint carrier fringes. Then you need to analyze that. And you do that in the Fourier domain. So you take your tilt fringes, you convert it to by Fourier transforms to the frequency domain. You select one of the sidebands, reject the DC and the unwanted other sideband, and you end up with what's called the analytical image, which is a way of directly getting the surface height. So here's a way of doing instantaneous interferometry, single frame, doesn't require polarization. All you do is introduce a bunch of tilt fringes. Well, that seems like a reasonable idea, but it was rarely used for decades. And the reason why is actually quite simple, because of the need for a strong computer to do that Fourier transform, particularly if you want to do real-time imaging, if you want to do dynamic interferometry. So there were some remarkable examples. Zeiss made a system where it was all firmware to do this, but essentially it was a lost art. I can remember having conversations with people and saying, well, what if we just use the Takeda method? And I was like, yeah, but that's not new. There's no invention there. Well, and besides, it won't work. It won't work. We'll have too many aberrations. I mean, there's a reason why no one is doing this. And so we just went in the lab and we just, no, this seems to work just fine. So we didn't invent it. But we realized through experimentation and a lot of work and work on the calibration techniques and so forth that you could in fact do this with tilt fringes. The computers were much faster. Real-time 4-megapixel Fourier analysis became available already in 2012. And so this old idea that was essentially in the attic next to the broken tricycle turns out to be something that you can apply today. Doesn't require any polarization optics. So with some clever calibration, the problem was solved. So that became our solution to the instantaneous interferometry problem. So now you can do dynamic acquisitions in a turbulent environment, and this is, I think this data is 15 years old. So some videos never lose their appeal, just like YouTube. So you can do averaging, and you can remove the effect of the air turbulence and find out what the surface actually looks like. And the nice thing for us is that even though it's not an invention, I would say it's not so much. But it is tremendously useful, and it solves for the vibration air turbulence, and it works with all laser physo systems. You just add tilt. So we have laser systems, 6 or 7 different wavelengths, for example. You wouldn't want to have a polarized phase shifting camera for each one of those. You just put in the tilt fringe. Now, I say just, there's an awful lot of engineering. I don't want to understate how much engineering is required to make this a good solution, but it's not really an invention per se. Okay, so I've given you some examples, so I'd like to leave you with a few final thoughts. The timing is good. If we think about what we do, we have to learn to do our jobs well. We have to understand the basics. We have to be able to apply what we understand to make things work. We have to be able to convince people to accept what we're doing and either fund our project or buy our product. And a lot of that involves creativity. And creativity is itself a science. There's a wonderful book, Creativity for Scientists and Engineers, that has a whole series of workshop type activities that you can do with, I'm talking to faculty now. The workshop type activities you could do to encourage the thought process that leads to innovation, that leads to creativity, thinking about things differently. It's really quite a good thing. Now, the other thing I'd like to leave you with is this whole question of where do our best ideas come from? I hope I've transmitted that nothing is invented in a vacuum. Sometimes the context goes back decades or even centuries to find out who originally maybe had the germ of the idea, which has now become this very practical thing that you've called your invention. So where do our best ideas come from? Well, it comes from the old books. You should have Ernst Abbe's theory of imaging formation in the microscope. These are the transcribed lectures that he gave. A wonderful, wonderful, wonderful book. Everything having to do with Fourier optics was taught by Ernst Abbe. You'll see everything in there. Fantastic. But also people from University of Arizona. The complex using computer-generated holograms to test aspheric wavefronts. So this is Jim Wyant. Some of the classic papers from this university, maybe you haven't read them yet, particularly those of you, their students. Go back and read those papers because you will see the insight and the intellectual energy that went into the early forms of these ideas that now have become commonplace. Now, there's this famous picture of Isaac Newton, and I have in the abstract, I say, well, he wrote actually an angry letter to one of his competitors. If I have seen little further, it is by standing on the shoulders of giants. That was Isaac Newton in 1676. So I have an update to this. And the update occurred to me recently when I was in Barcelona, and I got to go see the Castellers. Castellers in Catalan, in the Catalonian region of Spain, it's a sport, and the sport looks like this. You make a human pyramid, and these human pyramids can be up to 9 people tall, and their little children are at the very top. And this was at a practice session in Villafranca, near Barcelona. And I looked at that and I thought, this is how things get done. Everybody cooperating. And the people at the bottom of this tower are just as important as the people at the top. So I've updated Newton's statement. We stand on the shoulders of our friends, families, our colleagues, our coworkers, and all of those who came before us. With that, I'll leave you with that final thought.